As with many physics terms, work is, in physics, does kind of correspond to the English definition of the word, but not quite exactly. And we can see that with a lot of other terms as well. In physics, work is a force applied over a distance. It causes a change in energy for an object, and we'll talk more about that part of it a little bit later on. When I say it's a force applied over a distance, only the force in the direction of the distance counts. In mathematical language, work is a scalar, and it is equal to the dot product of force and displacement vectors. The magnitude of it, and since it is a scalar, we only care about the magnitude, is F cos theta times d. This cosine theta encapsulates the idea that only the force in the direction of the displacement counts. This theta is the angle between force and displacement. So if an object's moving to the right and the displacement's to the right, that theta is 0. Cosine 0 is 1, so then it just becomes force times distance. If a force is to the right and while the object's moving to the left, then that theta is 180, and the cosine of 180 is negative 1, so it becomes negative force times distance. You can have a negative work. And then, if the angle between the force and displacement is anything else, you take the cosine of that, and you get the component of the force that does work. Okay. Work is an energy. You see, it's force times distance. That is Newton times meters, and that is a joule. Joules are the units of work and of energy. It's the same thing. 1 joule is 1 kilogram meter squared per second squared. If you ever forget it and need to use dimensional analysis, that's what you'll come out with. So, on a conceptual level, we need to remember that we only do work when we apply a force in the direction of displacement. So right now, I'm sitting in my chair. Okay. And then I ask the question, am I doing work on the chair? And we know I'm exerting a force on the chair. There's a gravitational force acting downward on me, and because of that gravitational force, I am exerting a normal force downward on the chair. So I am exerting a force downward on the chair, but we know work is F cos theta times d, and d is 0. The chair is not being displaced, so I am not doing work on the chair. 0 work is being done. All right. Now let's say, now here's a kind of a weird example that messes people up. Let's say I'm carrying something. I have a book, and I'm holding my book and carrying it along as I walk, as I walk to the side. And then the question is, am I doing work on the book? Now, of course, I am exerting a force on the book. I'm exerting an upward force that cancels out the gravitational force acting on the book. But my force is upward. My displacement is horizontal. So my work is F cosine 90 times d. Cosine 90 is 0. So I am doing 0 work on the book. Even though I'm exerting a force on the book, even though the book is moving, I'm still doing 0 work on the book because the force I'm exerting is totally in the upward direction, and my displacement is horizontal. So remember, only work in the direction of displacement counts. Okay. Now let's say I lift the book. I'm moving the book upward. Okay. And let's say I move the book upward at constant velocity. Now what's my work? Well, my work, of course, is F cos theta times d. If I'm moving it up at constant velocity, that means acceleration is 0, which means the net force is 0, and the forces acting are the force from my hand and gravity. So if I'm moving at constant velocity, the force from my hand is equal to mg. So then the work I'm doing on the book is mg. Theta, remember, is the angle between the force and the displacement. Force is upward, displacement is also upward, so that's a 0, and cosine 0 is 1. And then d. So the work I'm doing on this book is mass times gravity times whatever that upward distance is. By the same token, if I move the book down at constant velocity, now my work is still mg cos theta times d, but now that theta is 180 degrees because the force I'm exerting is upward, but the book is moving downward, and so then I do negative work on the book, moving it downward. So this is work done by me. At the same time, what about the work done by gravity as I move the book upward? The force of gravity is mg. The work done by gravity is force times cosine theta. Well, gravity is down. If I'm moving the book up, that's cosine 180. It's minus mgd. And by the same token here, the work done by gravity is positive mgd. So the work, in each case, the work done by gravity is the opposite of the work I do lifting an object. And we'll talk more about that when we talk about gravitational potential energy. So now, another way of looking at this, another sort of application of this cosine theta is that work is positive when force has a component in the direction of motion. The work done is negative when the force has a component in the direction opposite of motion, and 0 when the force has no component in the direction of motion. So I already kind of talked about that, but I wanted to explicitly state that these three things, you can look at a problem qualitatively and determine whether positive, negative, or 0 work is being done just by the directions of the force and the displacement. Let's take our example of the inclined plane. Let's say we've got a block sliding down our inclined plane, and I want to know what forces do positive, negative, and 0 work. Well, we know what forces are acting on this block. We've got normal force, we've got gravitational force, we've got frictional force. Okay, so think about this. Our displacement is down the ramp. Okay, normal force is perpendicular to the displacement down the ramp. Ergo, it does 0 work. Okay. Gravitational force, if we break it up into components, it has a component perpendicular and then a component going down the ramp. It has a component in the same direction as displacement, therefore it does positive work. And friction opposes motion and therefore does negative work. Since friction always points in the direction opposite displacement, so friction or air resistance will always do negative work because they always oppose the motion of an object. Okay. Yeah, let's look at the same problem from a quantitative perspective. Let's say the mass of this block is 3.8 kilograms. Let's say the angle is 28 degrees. And let's say that the coefficient of kinetic friction is 0.21. And I want to find the work done by each force, not just the sign, but the number, the quantitative work done by each force as the block slides 1.3 meters down the ramp. Okay, so we can figure out the work done by gravity, the work done by friction, and the work done by normal. Okay, work done by gravity, is the force of gravity times the cosine of the angle between them times the distance, which is 1.3. Work done by friction is the force of friction times the cosine of the angle times 1.3. Work done by normal is normal force times the cosine of the angle times 1.3. Okay. Again, we know this angle is 90, so we already talked about the work done by the normal force is 0 joules. Okay. Gravitational force. Well, we know the magnitude of the gravitational force is mg. Okay. The trick is, what is this cosine theta? This theta, remember, is the angle between the force and the displacement. The angle between the force and the displacement is this guy. Okay. So that is the angle that goes in there. So we can say this is mg cosine, not 28, but 62. We could also say this is mg sine 28. You can think of it as being the component of the force in the direction of motion times distance, or you can think of it as the magnitude of the force times the cosine of the angle between. Either way, it works out. So that's just 3.8 times 9.8 times 1.3 times cosine 62, and we can figure that out. 3.8 times 9.8 times 1.3 cosine 62, that comes out to 22.7 joules. And then for the frictional force, we've got mu k times normal force, which in this case we know is mg cosine theta, times cosine theta. So this is the frictional force. Then this is the angle between, or 180, sorry. This is the angle between the friction and the displacement. That just gives us the -1 times 1.3. So then that comes out to 0.21 times 3.8 times 9.8 cosine 28 times cosine 180, which is -1 times 1.3. And we can punch that in. And we get minus 8.98 joules of work done by friction.